All right, folks, let's get started today. First, couple announcements. I made these all on Piazza, and all announcements will always be on Piazza, so look for those. Yesterday, one of the TAs hosted virtual recitations. The idea here is rather than having recitation sessions that you have to go to at fixed times, we're going to try virtual recitations where one of the TAs will host a virtual recitation section where they'll either go over the homework assignment or course content, kind of in a fixed lecture like a normal recitation, and then leave time for questions at the end. So we'll be announcing when those are. They'll change timing every week depending on which TA is teaching it and which TA is going to be covering that. We will record those, so you can find here Arvind held virtual recitation section going over assignment 1 and talking about that. So if you want additional help, please watch this and then look out for the next ones. The other thing that we're doing this year is the undergrad TAs are doing what we're calling assignment help sessions. So basically they will be in Brickyard 221 and they'll be offering help on the assignments from 1 to 4 today and from 6 to 7 tomorrow. So there's a number of undergraduate TAs. You can recognize them by their pictures on the website here. So if you're still working on the assignment, please head there and they'll be able to help you out. Questions? Okay, final thing, and this is very important. The grade that it shows on Gradescope is your grade. There's no hand grading or, oh, you mistyped a file name, we'll fix it for you. No, it has, just like when writing a program, either compiles or it doesn't. Your grades are what they are on Gradescope. And so I've seen some people have submitted things and they don't have an actual README file, they have a readme.txt file. And the grading system says that's a 0 because it's not following the instructions. The instructions say you need to have a file called readme. Not readme.txt, not readme.pdf, not readme.docx. It has to be just called readme. And it's giving you all of this output, so if you end up with a 0 and you will say, hey, but all I did was had this one problem, that's too bad. It's telling you exactly what your score is right when you submit or right a little bit after you submit. So it's up to you to know your score, and I don't know, you're going to be happy with whatever that is. Questions on that? All right, cool. Then let's move on to access control. So we've talked a lot about kind of overview of security. We've looked at security through different lenses, and now we're going to get kind of more into access control. So we'll get into it a little bit more in depth, but access control is basically trying to do, let's say, decide a policy of who should be able to access what. And so when thinking through this, I think it's a important thing to maybe go a little bit more concretely based on examples. So let's say we have some university who has an academic integrity policy. What would be a concrete example of such a university? ASU, yes, there's an academic integrity policy that you all are abiding to by being students at ASU. And as part of this policy, it includes copying homework with or without permission. So some CSE class has students do homework on a shared server. We can say it's similar to general.asu.edu. Student A forgets to read protect their homework, so they maybe whatever you could say, it doesn't matter, but the point is, in their home directory on this server, there's a file called, let's say, homework1.c, and they forgot to set the permissions such that other people can't read that file, so essentially other people can read that file. So student B then copies that file, because they just copy that file into their directory. Now they have access to it, and they submit it as if it was their assignment. So who did something wrong? Who?
Student B did something morally wrong.
Student B? Who violated the policy, let's say?
B.
Student B? Because why? Okay.
Because you leave the door open, or you unlock the door. You cannot enter the door without lock that.
okay, so student B is the one who copied the file. So if you take that analogy to a house, it's like even if the house was unlocked, they went inside the house and took something out of it or made a digital copy of it. So that's what that breaks down. Yeah.
Didn't the university also kind of violate the policy because they could have made it more difficult for A to share homework?
Yeah. Okay. So does anybody think the university's at fault? It's easy to blame maybe more specifically than blaming an entire university for the problem of homework assignment. Maybe the administrator of the server. Like what could they have done? Maybe. Yeah. Yeah. Maybe they can make the system have all files read protected by default. What else could they have done? Maybe student A didn't know that how to reprotect their file, let's say. Okay, so we're casting a lot of blame here. What about student A? Is anything there at fault? Yeah.
What, were you saying student A?
Yeah, student A.
Well, they forgot a policy instruction.
So they forgot a policy instruction? I guess that depends on what does the policy say, right? So yeah, this is kind of the interesting debate here that we can have. Is it, I don't know, is it just students B fault because they copied it, chose to copy it, or is it students A fault? And how do you, I guess, distinguish the case where student A deliberately makes their file read accessible so that student B can copy it, versus the case where they just forgot or didn't know how to do that? I don't know, should we just like everyone? Yeah.
We're going by the integrity policy. The only one that should be infringing on the policy itself seems to be, you can always cast blame around how set the context scenario, but in the end, it's who infringes on the policy, and then first time infringement of the policy is student B.
Okay, so then that argument is basically student B directly violated at least that snippet of policy that we have. Yeah.
But I think in like a real world application, you should always operate under the assumption that somebody's going to try to read your files. Like if you were to basically provide some real world companies, you should always expect somebody to try to hack their data. And
Right. So is that student A's fault then, or who?
I
Whose fault
would
is
say
it?
it's both of their faults
Both their fault. Okay.
in different ways.
In different ways. Okay. Yeah. I mean, again, I think it goes back to another point. Depending on what the policy says, right? If it says you can't share homework with somebody, that could be a violation of that policy, right? Even forgetting to reprotect a file could be seen as sharing. You know, I mean, to take that argument to the extreme, is it okay for student A to just post their assignment on the course forum and just say, well, this is how I did it. And then if anybody else copies from that, that's their fault. It's not my fault. Everyone copied from me. Yeah.
I think there's a difference between forgetfulness and malicious. If student A's fault could potentially have greater consequences because more people than just student B could get to the file, but it doesn't, in this example, it doesn't seem like student A wanted anyone to see the file.
Interesting. Okay, so yeah, so arguing kind of based on intent. So forgetfulness versus maliciousness. It's interesting. Yeah. Anybody else? Yeah.
The way that
You moved.
yeah.
Used to be over there. It's very weird.
The way that ASU's policy is written, I mean, intent doesn't really matter. Like for instance, if I was writing code here and the person behind me was looking at that code, it's still my fault, which I kind of don't agree with because it's unreasonable to assume that I can always protect it.
Yeah, that's interesting. To be perfectly honest, I don't know the intricacies of the policy. It's been a long time since I've read it. So one interpretation could be that the policy explicitly disallows sharing such to the level that even if somebody is, we call that in security like a shoulder surfing attack. So they're looking over your shoulder as you're typing your code, and they're either just like typing into their phone or maybe into their computer exactly what that code is, and that's your fault for letting them do that. So what are some maybe measures we could take to prevent this maybe from occurring?
show some maliciousness.
Yeah, so maybe there's mechanisms we can introduce in addition to this policy, right? We can say, have the mechanism be that every file that a student creates by default is prevented readable by everyone on the system. So that way that would essentially prove that you would have to take an extra step to enable it to be readable. That's interesting. Anybody have any other thoughts?
Implement DLP and document tracking.
Implement what?
DLP,
What's DLP?
data logging prevention, allows you to track files and information across the network.
Okay. Yeah, so maybe we could track that file across the network, right? Because there could also be, we also need to, I don't know, think about or worry about forensics depending on how malicious student A wants to be, right? They could just create a temporary file very quick that somebody else could copy, and then they delete that file right away. And then now there's they claim, well, I don't know how they got my file. It's read protected. Maybe they shoulder searched me, and that's not my fault that they did that. Yeah, interesting. So maybe through logs or other types of extra information, we could say, oh no, but we saw that this file got created with the content of this other file, and then the other person copied that over. Any other thoughts? Yeah.
Would you, theoretically, then tracking the downloads/access of that file across the server?
Yeah, so maybe tracking, so then more deliberate attempt, right, to kind of track where data is flowing through the system. Yeah, the trick is then how do you determine what is, I don't know, like if somebody's downloading the Linux kernel to compile it, you don't care about any of those files, you only really care about the homework files, and determining what those are can be tricky. Yeah. Cool. Awesome. Okay, yeah, this is a good thing. So we need to kind of discuss some important security concepts that are going to come up here in the notion and the idea of access control. So we have this concept of authorization, and it's kind of at the core of everything we're talking about here. So authorization here basically means what can you do on the system, right? What are you allowed to do? And what's one of the key elements in order to enforce some type of authentication?
Password?
Not necessarily passwords, more high level, yeah.
You need to be able to delegate or like assign certain levels of classification
You maybe to
Like
levels of
certain
classification to what?
to like the system or whatever, so that like you can assign like this person is like the janitor, so they don't.
Maybe, that may be a way we implement that, but to even get there, we're missing an important part. Yeah.
You need to be able to define who can use the system. Or
Yeah, we need to define who you are, right? If you just come up to the system and say, well, I'm the professor, and it says, great, here's all your permissions, right? How do we know that somebody's not impersonating us? So we need this other idea of authentication, which we're going to cover later, which essentially answers the question, well, who are you to the system? Right? And if we even think now, we'll go into it in more detail, but at a basic level, this is exactly what passwords and usernames are doing. Right? You register an account at the start with the system. It says, okay, I know who you are based on this unique username and password combination. And you can prove that it's you later on when you give me those same username and passwords. I'll know that it's you and not somebody else. Right? So that's how we can handle the who are you question, the authentication. And then the authorization can come in. Okay, now that I know who you are, what should you be able to access on this system? Cool. So really, and part of this, and when we're thinking about authorization, right, it goes back to even concepts we were already talking about in the overview. Right? We talked about, okay, well, who should be able to do what? It's kind of tied in a little bit of, well, what do they actually need to do their job? Right? So managing kind of trust and authorization, and also risk. So how can we manage risk through authorization?
Only give access to people who actually need the access.
Yeah, so only give access to people that need access, and there's probably a corollary there that's also important. Only give them just enough access, right? So access, we'll go into it in detail, but it's not a binary thing, right? You can either access it or you can't, right? Maybe they should just be able to read some information, but not write or alter or change it. Maybe they should so if we can use authorization, this idea of, okay, what should people be able to do, that can actually help us mitigate risk in a system, right? Especially in cases of, we talked about threats of insider attacks or insider threats. So what's an example of those? Yeah.
It's like when one of your engineers copies down everything they can access and then goes to work for your competitor.
Yeah, ooh, that's a good one. What was the famous case where somebody was alleged to have done that? The guy who went from Google to Uber with the self-driving car technology. Which one?
Edward Snowden.
Oh, Snowden, yeah. Snowden's actually another good example, right? He was I think an admin at the NSA, and he copied down a bunch of data and then released it publicly, right? So you think about an organization that should know the benefits of mitigating risk and least privilege, only giving people access to what they need, still fell victim to a problem of an insider threat that accessed more information than they should have. What's the balance here? Yeah.
You don't want to hurt the productivity of your employees if they have to go ask IT for permissions to access.
Yeah. Does anybody work at a company where you can't install your own software on the system? Yeah. Look around. There are hands up. You could talk to these people about how annoying that is, and how you have to do like insane workarounds. Like, I don't know, they'll do things like block Gchat, so you'll find some other way to use Google Chat in a different thing, or even if you think as a developer, if you had to ask IT and wait 24 or 48 hours for them to install some software, and you need some certain tool to do your job to fix a bug right now, that could be incredibly annoying. So you'll find ways around that problem very quickly. Yeah, so I think that's the other important thing to keep in mind here, especially considering what is the business, what are you actually trying to do. So that's part of risk, right? Part of the risk here is by limiting people's access to the system so much that they can't do their job or they hate their job, and you have huge employee turnover, then that could be another big problem as well. Right, and all of this is leading us to this notion of access control. Right, so authorization is what can you do on the system, and kind of the way I like to think about it is authorization is essentially the policy, who should be able to do what on the system, right, just in terms of what we've been talking about, and access control is the actual mechanism that's going to enforce that policy. It's a little bit more muddied than this, but we'll look at all different types of ways to model access control. We'll look at different access control systems, and we'll talk about the differences between them. But all of them are trying to implement and enforce this notion of who should be able to access what. And you know what the access control policy is like on your phones in terms of apps? So they ask you what? Right, so they can ask you for access to the camera, to maybe your files, which is great because that means it's blocked by default and you have to allow it. What other kind of access do they have, let's say, to the rest of the system? Like, are you worried that you download a flashlight app and then that app is going to steal all of your data from your banking app? Should you be worried about that? Yes, you definitely should be worried about that, right? Yeah.
There's proper sandboxing between applications, which application runs in its own environment, and it shouldn't be able to get data from other applications.
Yeah, exactly, right? So the idea is, and this is maybe basically like most operating systems, like desktop systems that we think about, Windows, Mac, usually every software you download and run runs as you, right? Which means you download some random app from the internet, from a site or a cracked version of some software. That's running as your user, which means it has access to all the files you have access to, which means all of your pictures, all of your documents, everything. And this is one of the key things that they learned when moving from desktop operating systems to mobile operating systems, is actually based on these concepts of authorization and access control. what access does an app actually need, right? So you should give it the least amount of access possible to do what it needs to do. And like we just said, the flashlight app should not be able to read the documents of the banking app. So they put really good restrictions, and they're sandboxing each app so that by default it can only access things inside of its app. It can't access any files from any other apps, which is a huge win. So this is why you don't have to worry as much. But then of course you download a flashlight app, and then what does it say? The Flashlights app is an old example because it actually was malicious on Android. There was an app that got super popular, and it turned out that it had malware in it. What it's going to do is going to ask you for access to everything, right? Or flashlight app is whatever, you already has a built-in flashlight functionality, but what about a game? Right? It's like, oh, I need access to your location, I need access to your pictures, I need access to your microphone. Right? All of a sudden you're giving this random app the ability to record you without your knowledge, to track all the locations you go and visit, to access all of your pictures. Right? And who knows what that app is doing with that information. Okay. Cool. And what we're going to first talk about is we're going to think about kind of access control in more abstract terms. So we're going to think about ways of how we can model access control, kind of any arbitrary system, and then we're going to look at different ways of enforcing that, and we'll actually be using this then in the context of the UNIX file permissions. So this is also a chance to learn exactly what all those bits are on the file permissions that we've been talking about. And basically, we're going to talk about this in several different types of objects. So we have subjects in our system. So subjects we can think of as just capital S, just a set of subjects. And these are things in the system that can act. So what would be an example of things that can act? Yeah. Users, what else? Groups, yeah, possibly. What else? Software, programs, yeah, your program that's running, right? Probably needs to act and do things, perhaps on behalf of users. And that's actually one of the things we're going to strip away about operating systems is actually on a Unix-like system, you as a user are never actually doing anything. You're asking other programs to do things on your behalf, and they're acting as you. So in those terms, everything is a process, and you're thinking about what can a process do. So objects, so then we have things that can act, and then we need some kind of notion of assets or objects in the systems that can be acted upon. Right? We'll use this idea, the capital O object, so it's a set of all the things in the system that can be acted upon. What are some examples? Files, what else? Pictures, what else?
Block devices.
What was that?
Block devices.
Block devices? Ooh, interesting. Okay, so yeah, maybe like block lists or any kind of like operating system level data that's important. Yeah.
Data tables.
Data tables, more example? Or
Like if you have all of your user information like a SQL server.
so the operating system, let's say the operating system's data itself maybe, or the application's data, it may not be in a file, or it may be stored in a database or something else which actually stores in a file or many files or whatever the details aren't that important. Yeah. Your webcam? Yeah, is that something you want other malicious people to be able to act upon? Yeah, you want to be able to restrict who can access that and what happens, right? Yeah.
I/O devices, like your mouse, keyboard.
Yeah, mouse, keyboard, printer. And yeah, these are all great. But then we have, okay, so we have things that can act. We have things that can be acted upon, right? We have our subjects, we have our objects. And then we have some notion of rights. So basically, what can the subject do to the object? And what these things mean are dependent on the system, right? So if we think Unix for a second, what does it mean when you have read permission on a file? That you can read the contents of that file. What does it mean if you have write permissions to a file? You can change the content. You can also delete the file. So deleting, I believe, is inherent in writing. What about in terms of directories? What does it mean to read a directory? lists the contents of that directory. What about writing to a directory?
You can change it.
What's that? I don't know. That's an
Adam delete.
well, I know for a fact you can't remove a directory unless you can remove anything in the directory. If you have permissions to, but there may be a directory that you have write permissions on that has a file that you don't have write permissions in it that you can't delete. Yeah. Yeah.
Can make new files.
You can make new files, right? So this is why it's important to understand the system that you're actually talking about, because you may think permissions like read and write are very clear and straightforward, but actually on a given system, depending on the object, it could mean something very counterintuitive. Like writing to a directory means that you can create new files in that directory. Cool. Awesome. And I'm going to start drawing now. So everything has backup on slides, so don't freak out too much. My handwriting's not the best, but I try. All right, so we have, so let's say we have some system. Our subjects are, man, this is out of practice, I guess. All right. Okay, so somebody give me some subjects, like short letter names.
Cat.
No, short, like one letter.
Oh.
A,
Z.
Z. There we go. I wasn't gonna go with B. Lame. Okay. So we have a set of objects.
B and
R,
Y.
Q. All right. And we'll say a set of rights.
X.
X,
W.
W. Yeah, we're not gonna use the same letters here. Okay, so now this system is basically complete, right? We know all the subjects, we know all the objects, we know what rights exist. Now, how should we be thinking about who can access what? Or when we think in terms of access control, right, what we mean specifically here is which subjects have which rights on which objects. Right, so how can we be thinking about this? Oh, much better.
SRO. Maybe like ARW on that.
So we could say what? So A on object R. So we'll just we'll do this for now. I'll maybe fix it a little bit. So we can say subject A has rights, which is going to be this set on object. Ooh, that should be lowercase r. R. So what rights do we want subject A to have on R? What is it? X? Just X. Okay, what are our options?
X, W.
So it could be X, it could be W. What else?
X or X and W or neither.
X and W. What else?
Neither.
Empty. So what does empty mean?
Can't do anything.
No rights, right? We have no rights on that object. And XW would mean we have all rights on that object. Cool. All right, let's bring this up. We can maybe call it, I don't know, AR. So if we wanted to do this, what could we keep doing? So we can set up the rights of object A on Q, right? Which is going to be something, null. And then we can set up the rights of Z on R. Give it at least W, yeah. And then ZQ, WX. Ooh, there we resolve them. See, better that you're doing this than me creating that in advance. Okay. But this is a little bit, can be a little bit unwieldy to think through. Or another way of representing this is we could basically create a matrix of subjects objects, right? And we can put in each cell what rights the subject has on that object. Yeah, cool. So we can do here, we have our grade, so we have A and Z, and we have R and Q. And then I can just put in here, AR was Z, X, AQ was empty set, so I'll just put nothing there. ZR was W, and ZQ was XW. Cool. So, and we're kind of, so an interesting thing to think about is, can A ever do anything to Z? Or can A do anything to itself? Can a subject also be an object? Yeah? Can somebody give me an example? Software, what kind of software? Concrete example. Too vague. Yeah. A word processor, okay. Then give me, concrete example. Why is the subject an object there?
It needs to edit itself. Like you need to open a file inside the program and then save it to an internal database of the software.
So you can open up the program itself in Word?
No, like it needs to edit its like resource files so that it can keep track of changes that have been made.
Okay, so changes, yeah, I think that you could torture that and it would work. Yeah.
Like a user profile on a website, things like an admin maybe.
Okay, a user profile on a website? Yeah, that's a good example. So, which may be actually similar to the Word example. So, you have your Facebook account, you can edit. You can also maybe think of maybe those are just objects though, right? Maybe those are objects. Your profile data is an object on the system, but it's not actually the thing that's acting. Although maybe you could say the thing that is acting that you can change is maybe your username and password, or changing your email, which is an inherent part of your identity on that system. Yeah, what else?
I don't know if this is right, but what if like you have a terminal that's hardwired to a system so that only that terminal can access it?
Okay, we're thinking about terminal systems. So if we think of the UNIX model as a process is the subject, right? So a process that's running on the system can do things. A process can try to kill another process, right, to terminate it. A process can also send signals to another process. So there's permissions basically there, yeah.
So going back to the other text editor, like wouldn't that become a user when you're calling it for print that now it's sending a signal to the printer?
Right, so then a subject, yeah, that's interesting. Okay, yeah, so yes, so then you have, if you have peripheral devices like a printer, and that would be one subject, and you've got another subject of your, although do printers act? That's an interesting question. I don't know.
Printers can.
Huh?
You can use printers to access like your link Wi-Fi and like the network traffic.
Yeah, okay, we can go with that. Yeah, that makes sense. So I'm convinced. Okay, so yeah, we can have the printer be a subject, and so we have to have rights, and we want to mediate access between the web, text editor and the printer. Yeah, that's great. Cool. So now we need to. So in most cases, that's what we want. Again, it depends on the system itself, right? So we need to extend this with A and Z, right? What rights do they have on each other? And for right now, we'll just keep it, I don't know, I'll just throw randomly stuff in here. Cool. So here's just another example. I mean, this is in the slides, so you can review it later. Here's just some system. And the nice thing here with this access matrix model is I can represent all of the access control rules of this system. So if I asked you, does V have R1 rights on object G, what could you say? No, right? Or, you know, every answer to every access control question you have can be answered very quickly using this matrix, right? You can look at this. You can also, one of the other nice things is you can answer questions like who has access to file G? Just you, right? Not V. Or who has access to V? or who has rights on object V? No one, right? So you have all this information here contained within this table that is very easy to see and understand. So now we're going to actually make this more of a concrete example. So we're going to go to the UNIX model, and we're going to talk about, so we're going to think in terms of subjects are a process. So every process that's running on the system is an object. And we'll think about files as objects. So you can think files and directories, maybe they're the same thing. Maybe a directory is a special instance of a file. And the rights that we're thinking about are basically read, write, execute, append, and own. So we talked about maybe read and write in terms of files. What does execute on a file mean? Be able to run it? Yeah, so and it specifically, what does that mean to run it?
Perform the action.
Maybe perform an action depending on what the code is, but how does that happen in our system? Yeah.
It creates a process.
It creates a new process, right? So which actually adds to our system, right? So the other important thing to think about, these aren't static systems where we just have a fixed set of subjects or a fixed set of objects. This is changing based on what's happening on the system, right? So if the process executes a file, that actually creates a new process that has the code of that file that's running. What about append? What's the difference between append and write? Yeah, so append means we can add to the end of a file, but we can't change what was there on that file. Whereas write permissions, we can completely change the file. Why do we care about that distinction? Yeah.
For like logs, if you want to keep track, you want someone to be able to add something new to the log, but you don't want them to be able to go back and change stuff.
Yeah, so logs are great for forensic purposes, trying to understand what happened to a system, right? If we know the system can enforce the fact that logs can't be just deleted by the attacker, right? The logs just always get appended to. That way, whatever the attacker does, they can't delete or remove those logs. Cool. Then what about own? Yeah.
What process like created it or started it?
Yeah, so on a file, well, yeah, I think created it is a good way to say that, but it doesn't necessarily have to be the case because you can change ownership, right? But yeah, essentially who owns that file and what does that allow you to do on a UNIX system if you're the owner of a file? Yeah. Change permissions. And what does that do in our model? Yeah.
Just like let yourself do whatever you want. You can change the permissions for anything.
Yeah, so in our model, right, so you decide what the permissions are for that file that you own. Right? If you have ownership permissions of the file, you can decide that other people can read or write to that file or execute it. You can even change owner. You can give ownership of a file to somebody else, and now you no longer have it, but somebody else can. Yeah.
Also, it's basically changing the access matrix. Is what you're saying.
Exactly. So it allows us to change. So having ownership rights of a file allows us to change access on that file.
And next question, going back to execution, does it change an object to a process?
Let's say it creates a new process based on that object. But yes.
Oh, sorry, I meant object to a subject.
Yes, object to a subject, exactly. Yeah, with our model, they're the same. Cool. So we have read, write, execute, append, own. Right, this is a simplified version, and we'll kind of go into why that is in a bit. So let's build this up a little bit. So we can say our subjects are, we have A and B. And subjects, and we have our objects. All right, so I can create a quick matrix here. Okay, so I can have maybe a simple system like this, where I have a process A, a process B. I have two files on the system, a homework file and a public file. So the public file is readable by both A and B and writable by A. And the homework file is owned by B and is readable and writable by B. So now if we go through certain things like and we can reason about how this model changes. So we can say things like, okay, can A access the homework file? Read the file? No? Can they write to it? No? Is it possible, based on what we know about the rights of a file and how this system works, is it possible for A to read the homework file?
Yes.
Yes. How?
B changes A's permission.
Yeah, so B owns the file, right? So B can change the permissions of the homework. We haven't defined it. We can define a function of change, we can think of it now of chmod, so that's basically what the file you've been, or the command you've been running on UNIX that allows you to change permissions of a file if you are able to do so. So we can say B runs chmod of homework, A read, and then what happens to this matrix? Yeah, R. Cool, so now A can read it, awesome. So let's go back, assume this doesn't happen. Now what if I take away B's right to own this file? Hello, no, I don't want that. What if I take away B's access to this file? Now I can ask two questions, right? I can ask the same question. Currently, is it possible for A to read this file? No. Can it ever be the case that A can read this file?
Yes.
Yes, how?
If somebody on the system gets root or pseudo permissions, they can just change ownership.
There's nobody else on this system. It's only A and B, and we're assuming that everything else is perfect. So we're just going based off this policy. So.
Isn't there an assumption that every file needs an owner?
No, because I just said so. It's a simplified Unix model, so you don't need to introduce complexities like that. We could assign the ownership to nobody or something. I don't know. So is it ever possible that in this model, A can access this file? Yeah.
Yes, inheritance is like a file that he creates and you do something inside the file that A has permission to read.
Ooh, okay. So
I'm sorry, I didn't hear what you said.
yes. So the idea is, well, we don't. Okay, so right now we don't have a new file. right? So if we had a new file function, okay, then let's walk through this. So we have a new file function. Who does it? Let's say is B. They want to create a file foo. Okay, good. We'll take this step by step. So that's all this does is allow them to create a new file. And by default, let's say when you create a new file, you are the owner of that file, and that's the only permissions you have. Right? Nobody else has permissions on that file. So B says, okay, new file foo. What does that do to my matrix? What was that? Put a new object, which adds what to my matrix? A new column called foo. And then now the permissions based on the semantics of new file that we just said is all it is O. So that B is the owner of that new file. Okay. Yeah.
I see where we're going with this, but this is arbitrary. I mean, I could print it, the file, and show it to the guy. It's not going to change the fact that he can't access the file.
Yeah, it depends on, well, let's keep going with this, right? So B can access this file, create a new file foo. Then B can do chmod foo. So B is going to do chmod B foo. I'm going to say that now B can write to this file and read. We'll say write and read. So B is going to give itself write and read access. And then we'll do another chmod B that foo. Yeah, so to foo that A can now read it. So assuming we have the ability to read the contents of the homework file and write them now to object foo, can A read that file? Yeah, so again, this is, so to answer the questions we were just talking about of is it possible, right? What's really important is the semantics of what can happen. Because if I say, well, sorry, on my system, you actually can't make new files. Like, sucks to be you. You have to deal with the files that you're given. So if you can't make a new file, is there a way for A to read the homework file? Yeah.
Do you get file copy permissions with write or read?
Do you get file? Yeah, that's another interesting one. I'd say that's inherent with read. Like a copy you can think of as read from one file and write to another file.
Could be copy homework and create a new homework that B would have ownership of?
Can't create files anymore, so no more creating files.
Okay.
Simplified, very simple. Maybe to the point of not usable, but.
So
The only way that it would be is if B had write permissions to cover it, so A would read from there.
Right. So this is kind of the what we're getting to here is if we think of this just in terms of a model, you can talk about all the formalisms of this, and if you have all the specifications of all the ways to update this matrix model in a formal way, you can actually prove a statement like that. You could say that it's never possible that A can read the contents of this file, right? And so. So this is why we think about, so A, it's nice to reason about access control at this level, that we can see the whole system, we can see who can do what. The more difficult thing to do is reason about how the system can change, and you have to reason about all possible ways that the system could change. But the nice thing that this allows you to do is if you think about things in terms of this, this model, you can actually prove interesting properties of an access control system. You can say it's never the case that A can do this. And again, your complaint may be, and I think it's reasonable, that, well, but this is hiding a lot of complexities of a real system. Like you just said I can't create a file, so who's going to use your system if I can't create a file? Right? Which I definitely agree with, and this is, again, maybe the trap that comes in from, there's a joke, maybe you've heard it, and I'm probably going to butcher it, but there's a joke that a physicist, or I don't know, whatever, but I'm going to ruin it because I just forgot to set up. But the idea is if you're trying to punchline is assume a spherical cow. So that's the punchline. Because physicists like to deal with a simplified, and mathematicians, a simplified model of the world. So if you're talking about a cow, they will say, well, assume a spherical cow. That's the first step, right? So it's like this. Like if you want to be able to formally prove something, you need to make crazy simplifying assumptions about the system, which may not hold in actual practice. Cool. And okay, so yeah, so then let's talk about and think about what are some of the benefits and drawbacks of this type of access control model, this matrix, using this matrix model. And we can talk at the high level, right? We can, at what we talked about just a little bit right now, we can also talk about at the implementation level, or actually let's talk about that in a second. So we'll talk at a high level about what are some benefits and drawbacks of this model. Yeah?
If you have enough users, it might just not be feasible.
Yeah, if you have enough, how much would be enough, do you think?
It depends on how big your database is.
Okay, so maybe for implementation reasons, but what about, let's say, being able to reason about the correctness of such a system, right, as a human? Right? If you have 1,000 users and you have 1,000 rows, being able to say, does this access control mechanism actually enforce the authorization policy that I want, can be a difficult question to answer. Right? What else? Yeah.
A benefit would be it was a lot easier to read than the previous model we showed them.
Yeah, it's a lot easier than just having these pairs of a subject-object rights, subject-object rights, subject-object rights, right? It's a little bit more difficult to reason about. If you can see exactly, if you're interested in one particular file, you can see all the access to that file. If you're interested in one specific subject, you can look at the row and see everything about that subject. Any other benefits, drawbacks? Yeah.
And you said earlier it doesn't account for changing states and then it hides complexity.
Right, so yeah, then there's the other problems that we faced of how do you actually use this model such that it represents all of the functions, like all of the actions that subjects can take on objects in your system, right? So you need those defined, probably formally, so you can reason about them, and they need to actually map what's actually implemented. Cool. Okay, so now let's talk implementation. So how would you implement this? Let's go back to the example. Right, so think about a system, an operating system, right, moderating everything. What do you actually need to do to implement this access control and access control matrix? Not a lot of hands. It sounds like it'd be a fun assignment. More people will. Yeah. Sorry, can you be louder?
Would you just do a bunch of chmod commands?
So sure, you could do a bunch of commands, but where is this matrix stored? And who checks that you? So chmod commands, right, allow a process to change the rights of a file, but where are those rights stored? Yeah.
Do we need some kind of super user to maintain this?
Yeah, we need so one question would be, where does this live? And who updates this? Where does it come into the system? How is it created, instantiated in the first place? And then who's updating it over time, right, as chmod comes in? You wouldn't want necessarily an administrator, a human, doing that every time. That would be a little bit insane. Yeah.
I was going to say, is it stored in root?
Yeah, so, or the operating, you can think of the operating system and root as essentially the same thing, right? So a root is the administrator that has access to the whole system, and that includes the operating system. So ideally, so kind of what we're getting to here is if you think about this just as a data structure, right, as a matrix, what is a matrix in terms of a data structure that you're used to in programming languages?
An array. Two-dimensional array.
Yeah, a two-dimensional array, right? That's all it is. It's nothing complicated. You've been doing that for a long time, right? You just store that somewhere in the operating system. But the important thing is you don't want any of these subjects to be able to just modify it, right? Your system was such that anybody can go in and change this table and add any rows. You don't have any kind of security mechanism. So you need, let's say the first implementation thing is you would need this, you would need to ensure the integrity of this access control matrix, right? So that would be the first priority. You could do that by, let's say, it's part of the operating system, so only the operating system and administrators can mess with it. Maybe we start there. What else? How else would you implement it? Yeah.
You'd have some isolated service that you connect to that like handles all of the permissions changes.
Oh, interesting. Okay, so you can actually store it off of the system in another system,
Yeah.
right? That's interesting. Yeah, that's kind of how, I can't remember, like Active Directory basically works that way, and other systems, I can't remember, I want to say Kubernetes, but I know that's wrong. It's some system that starts with K, but I can't remember. Kerberos, there we go, yes. Kerberos kind of works the same way as well. Access control happens on one central machine, and the other machines essentially delegate to that system. Yeah.
Isn't there like a parent-child relationship where it's like a parent has access to all the files, but the child only has access to some of the files of the parent object?
Possibly. I mean, you could create the tables to enforce some kind of inheritance or something like that. Yeah, that's definitely possible. What about, think about it in terms of actual implementation. So we just talked about it, right? A two-dimensional array. So you have a system, let's say all of you, there's 373 of you currently in this class, rounded to 370. So if I had to create a system for all of you to use, how many users would I have?
370.
370, so it'd be at least 370 rows if we just think in terms of users and don't think about a process right now. Then what happens if one of you adds one file?
You need to add 370 cells.
Say it again?
One column?
Yeah, it has to add one column, which is 370 additional cells you could think of. And then if you create another file and more users, so on a typical system, what's going to be bigger, the number of users or the number of files? Files, they'll be a lot bigger, right? Every application you install has dozens of files. Each of those needs to be a column in your matrix, right? And then when you add a new user, then what has to happen? Yeah, it has to be a new row with all of the permissions. So you create a new user. You have to think through now, well, what permissions should they have on what files, right? So no permissions to anything. Yeah.
It'd be classified like a set of 70 rows. So you have one row that's like a specific type. You could lump everyone in like that set.
Yeah, but then I get into tricky things like how do I make sure that you can't share files between each other? If I just considered you all the same subject, right, as like a student, then I'd have to think through, well, how do I make sure that, like, we talked about the copy protection example, right? How could I make sure that you can't transfer files from one user to the other? So yeah, one option would be simplify the matrix in some sense. Yeah.
Couldn't you like create a hash with every like user having their own like base key and then a bunch of different like for every file they have, you have a new key value with permissions?
We'll talk about it more when we get to crypto stuff, but there are some things you can do, but it becomes tricky. But essentially, there's a couple different things to think about. One is this, essentially this giant matrix is really great for reasoning about what should happen. It's also great when you're thinking about a simplified model of a system so that you can actually reason about what's going on. In terms of real systems and in terms of real implementations, I don't think anyone actually implements it like this, like we talked about, right? Because of all the inherent challenges of, man, when you add a new user, that's gonna, as the number of files increase, if you have a server with, 500 terabytes worth of files, right? Now you have this row, you end up having so many columns that adding new users would be kind of insane. And you can use some tricks. There are tricks with, a sparse matrix or whatever, but still, if you need people that have access to things, it can cause a huge problem. So the interesting thing is we could actually split up, rather than thinking about this matrix in monolithic terms, we can look at it in terms of different ways. So we can, for instance, what if we just look at every, what is this, a column? What if we look at every column? right? So rather than, let's say, storing in one place in the operating system this huge matrix, what if we stored with every file the list of people that can access it and what rights they have, right? And you could think that this is, again, the key tenet is that nobody else can modify it, so it's kept by the operating system. But the operating system would keep metadata about the homework file that user A has no permissions and user B has read and write permissions. Yeah. So this is a basic idea of splitting up this matrix so that rather than thinking about the whole thing, we can actually implement it and store it in terms of columns, right? We could say, okay, for a given, and we could maybe even do some nice optimization saying, well, if a user is not in the access control list, then that means they have no permissions. Yeah.
Wouldn't that make checking like what permissions the user has on any given object like take a lot longer?
So let's think about that. So I'm user A or I'm process A, right? I'm trying to access, well, okay, this is a wrong example. Let's say I am process P. I'm trying to read to the G file. Should that be allowed or not? Yes, and how would you know as the operating system? Pretend you're the operating system. What do?
You just check G files, metadata.
Yeah, look at G files metadata for the access control list. You look in this list, you say, is P in this list? Great. What access control does it have? R, and this is asking for R, so this means that that person can read this file. That's good. I'll allow that access. And it's pretty quick because you can implement these in terms of hash tables, so it'd be a constant time lookup, and you won't have to scan the whole list, and it could be very nice. Yeah.
Would you also have to add an object for each user? Because CPU likes to control our rights over that user.
Yeah, we'd have to think about how do we do that with subjects, right? So we could think the operating system could also keep metadata about a process, about what rights other users have over that process. Yeah, so it's the same notion of for each object in the system, which includes subjects, we need to store metadata with that object about who can access that. Yeah.
When you LSLA, is this what you're seeing?
Yes, but a simplified version, and this is what we're going to get to of actually implementing this versus how it actually works. But yes, this is why essentially on Linux, every file has the access control list of who can access it, but a abstracted version. It's not a list of exactly every person on the system who can access it. So if we take this same notion and we think about splitting up our matrix in terms of columns, what's another way we can split it up?
Rows.
What was that?
You said rows.
Oh, good. Way to steal somebody's answer. I think that's against the academic integrity policy. No, I'm just kidding. Rows. We can think about it in terms of rows, right? We can store with each subject every object that it has access to and what rights of those objects, right? And of course, again, the same idea, we wouldn't want them to be able to tamper with and change their access. So kind of historically, these are called different things. So like the access control list is the column. So every object stores what subjects have access to it. Capability lists are the other notion of storing the rows. So every subject has the list of objects that it has rights to. And again, same thing. The operating system now, process P says, here's my capability list. I would like to have read access to file G. And the operating system will look at the capability list and say, yes, you do have read access to file G. Great, access granted. What are some of the differences between these two? Besides columns versus rows. Yeah.
If you store it with the subject, the other user can create a file and then has to update a file in another user's kind of domain.
Yeah, so the system, so this is where things get a little wonky and weird, right, in terms of updating. So if we have this type of model, if subject Q creates a new file that subject P has rights to, all of the subjects' capability list needs to be updated with access to this new file, right? And conversely, the same idea actually also applies to access control lists, but not when creating a file, because when creating a file, you would just put who has access in the access control list. When do we need to go through and update everything? A new user, a new subject is added to the system. We'd have to go through every single file in the system and add those rights that that user has. Yeah.
Can you just like ignore any new things until they're encountered, and if it's like not present in the list, then you just assume there are no permissions?
Yeah, but you can't have it both ways. So if you want to assume that something in the list means you don't have access to it, then you don't want to have it also be the case when something's not on the list, you look up and do more additional work, right? Yeah, maybe, I don't know, you can think of maybe ways to optimize it, but if you think about it just in terms of a fundamental model, it's a little bit more difficult to think about that. Yeah, so these are basically kind of inherent pros and cons. Changing different aspects of the system causes different problems, yeah.
So like when a user accesses a file or a directory, is the computer like checking these,
Yes.
both of these, or only one?
So yeah, usually you only do one, although you may be able to configure a system to use a combination of things. I think the sky's the limit in terms of implementation. But yes, on like a Unix system, Unix uses access control lists, and so every time you ever edit a file, you ls a file, this actually happened to several people, which I still don't understand how, but if you ever figure that out, let me know. They created the .ssa/config file in their local home directory, but the permissions were set up so that they, as a user, had no read permission to the file, only write permission. And then when they tried to SSH to bandit, they couldn't read their own file, so it never got set up and the config wasn't happening correctly. So just either deleting that and starting over, or changing the permission so that they could read their own file actually allowed everything to work. Yeah.
I noticed that happened on Windows when you install Windows as a subsystem.
Oh.
And you create it, that gives you the access outside of it.
That is fascinating. Yeah, this Windows as a subsystem thing seems to be causing a lot more problems than I had hoped it would. But
They do it.
oh, please.
I've seen weird problems with people trying to install or update things as root, and then they can't reach it.
Yeah, that makes sense because installing things as root, you're now a root user. So when you create a file, it's owned by root, and so by default, other people shouldn't be able to read that usually. So yeah, that can cause massive problems. Yeah.
Question about these lists.
Mhm.
Is there another type that stores like the objects and then has, I guess, a bunch of different rows for each permission, and then in those rows would have a list of the users that have that permission? That
Oh,
seems like it
in
would be
those
better
terms?
because you rarely add new permissions, right? So like
That's
you wouldn't be
interesting. I think for most cases, because you may want, a lot of times you're not just opening a file for read, you're opening a file to read and write to that file. So rather than looking up two different permissions, like rights on a file, you'd want to say, what rights does this person have on this file, and then use that as terms of a set. But yeah, that is interesting. I think you could think about that. I'm sure it could work. Yeah. And another type that's actually the type that we already talked about is kind of a relational table, which kind of goes up to what we were talking about. Basically just subject, access, object. So, or any combination of the order doesn't matter so much. The idea just being that we could think about it of listing exactly how we did, and this is where we started from, subject, access, object. And so you'd look up, you could look up subject and object, and it would tell you all the access that they have, all different types of things. So let's see, some interesting aspects here. So for an access control list, we need to be able to know the identity of users, of subjects. So we need to make sure that we know some way of subjects. The interesting thing about capability lists, and we'll get to this more in crypto, but we don't necessarily, if the system, so this is actually where the Kerberos model comes in. So with Kerberos, you don't authenticate to the system you're trying to log into. You authenticate to a third system that issues you some cryptographic ticket that says you have the capabilities to do X, Y, and Z on this system. So you then present these capabilities to your system, and then it says, great, you have these capabilities. So that system is not ever verifying your identity or who you are or checking username and passwords. It is trusting these cryptographic tokens, these cryptographic capabilities of what you're allowed to do. But this can cause problems, so this is why, we'll get into those more in detail later, but it's another kind of interesting way of thinking about this problem. And this is why systems that use that model, like Active Directory and I believe Kerberos, will allow you to use these capability lists. Cool. Yeah, so I think this is just a graphical representation of the two different systems. You have many files in a directory, and each of the rights will be on there. Okay, we'll get to UNIX access control. Oh no. Okay. Okay. So other types of things that we can think about. So for capability lists, we can, when thinking in terms of least privilege, so we can think the security principle that we want to provide that objects should only have access to exactly what they need to. That when let's say the system grants a subject capabilities and a capability list, they can give them just the capabilities that they need. Rather than, as we mentioned, going and updating every single file to give that subject access to exactly what they need, you can actually have a much more fine-grained thing, especially if you have like a backup service that's just running once a week. So the backup service spins up, it's a new subject in the system. Rather than giving read access to every single file in the system to the backup system, the operating system can just give the backup subject, here's a capability list that says you can read every file. And then it goes away as soon as it's done. You can also do cool things like doing expiration dates on those capabilities and all kinds of cool stuff. So what about trying to review these systems? So we said one of the nice things about having this matrix is we can actually try to look at it and review who can access what. So what about these two systems maybe changes that notion of access review? Yeah?
As the systems get bigger, it's harder to review who has what permissions.
I'd say it's true in both models. Yeah, as the system gets bigger, it becomes much more difficult to review. Right? But let's say in a capability model, we want to say who has access to a certain object. What do we have to do? Yeah.
You have to look at every single user.
We have to look at every single user's capabilities and see does anyone have this capability, right? So in that sense, an access control list can be better, can enable better review of objects, right? We can look at an object, we can know exactly what subjects have access to that object. But the other way also works in reverse, where a capability list, we have better access review of subjects. We can say, okay, what does this, this subject, this person, what can they access, right? Otherwise, we have to literally scan the whole system, look at every single file to see what things they can access. Again, the idea of revocation. So what do we mean by revocation here? Removing access, right? Revoking access. So again, similar idea. If we want to revoke access to a certain object, we can easily do that in an ACL model. We can remove everyone's access just by modifying the metadata of that object. And capabilities are better on a subject basis. Okay, we're good. So when we come back on Tuesday, we'll talk about the UNIX access control list. We'll actually look at exactly how that works.
See you guys.
See you, Judy.